Okay. So we can meet.
Okay, so I'll give a short introduction to quantum map correction in the next however long it is, like 70, 90 minutes. And I'll try to give a bit of a progression between like some of the basic stuff, basic codes, and then hopefully in the end all the way to doing multiple gate operations, all of these in a setting of how we typically in practice think about these types of error correction problems. So maybe the first thing to start with is errors. Right? We need to correct errors. We want to correct them. So we have some here I'm just trying to illustrate the blocks here. So everyone is familiar with blocks here. Yeah, please interrupt that. We have some vector psi, which characterizes the quantum state. For now, let's just think about a single qubit state. And then some errors happened on it. This wanders somewhere. And now your state vector is different. So an error might apply some generic channel which transforms the state. So this at first sight might feel quite bad, right? Like there's a continuum of different error possibilities. That certainly seems to be pretty challenging to deal with. Also another thing is that when we so we have this continuum of errors. Not clear how we correct that. We also have the problem that maybe measurement might actually collapse the state inadvertently. Like when we're trying to figure out what errors may occur, we probably want to do some measurements to extract information. How do we make sure that the logical information that we're interested in is not just looked at the same time? That's another issue. Actually, maybe I'll correct this now. I haven't given that many boards. So challenges of running QC. So continuous errors. Measurement and collapse the state. And then another obstruction is that there's no cloning theorem. So if I have an unknown quantum state psi, I can't just directly use some gate operation to transform this into a product of difference. This basically would correspond to cloning an unknown state. So this also presents a challenge in terms of at least naively thinking about quantum error correction, how exactly to do that. Does that make sense? So how do these challenges get solved? It's actually pretty amazing that quantum error correction works, actually all of these turn out to not be issues. So for the first thing, we have these continuous errors, but the key trick is actually that these measurements actually come to help solve this one. So essentially, the way we're going to solve this one is that measurement projects the error. Into a discrete set. So the measurement actually projects things into only a discrete set of errors. Maybe just to very simply illustrate it here. So we have some target state psi. And let's say we measure in the z basis, we're just effectively projecting onto the z-axis. So if we measure the original state psi, we'll get some distribution of like up or down. And if we actually measure this new state, okay, it has a different z projection, but you're still going to get an up or down result out. Right? So effectively, if we think about the actual effect at the end of the day when we're doing measurements on the system, then either it's like erroneously flipped or it didn't flip. And so in that sense, you actually, when you're measuring the z basis, you effectively discretize things into just like x errors or no x errors. And actually the same thing turns out to hold more generally. Essentially, the measurements actually project you into a set of discrete. So that's how the first one gets solved. The second one, okay, so measurement does have this collapsing effect. So you basically want to be clever about what you measure. So you want to be able to capture some set of, you want to be able to catch the errors without actually collapsing the logical information. And so therefore, when we design the quantum error correction code, we'll be very careful in order to make sure that doesn't happen. And then finally, for the no coding, really, I think it's more that when you're encoding, you're actually not repeating the unknown state. You have some generic state that you're trying to do computation on. Actually, you don't want to repeat that unknown state multiple times and then do checks. Instead, you encode this psi into some more complicated psi. Let's call it psi prime. Or call it psi alpha.
Could you use something other than green?
Oh, okay.
Also, I wonder if it's better if you bring it to the middle since there's a light right now.
Yeah. We'll put it into some other states where relevant information or like space where our logical qubit lies is still same size. So essentially, and can everyone see down here, or should I stop a little bit? Okay, yeah. So essentially, we're working in a larger space and only using some part of it for computation. So the amount of like logical qubits is actually the same as our target information size, and we're using the rest of the redundancy to help. So that's how we'll eventually get and handle all of these naive challenges. Okay. Great. So with that in mind, let's start going into concrete examples just to get a sense of how these actually pan out in practice. So with the first one, I'll start with the repetition code. And this is, of course, a classical code, but it will actually illustrate most of the basic principles that we care about. So we have some initial state, A0 plus B1, and then we'll encode it into, let's say, 4 qubits here. Okay. And actually, I've also illustrated it here. So this one, actually, let's do this one. So this is the 3-bit repetition code. So this one is a qubit. This one is this one is This one is also a qubit, but it has many different names that are sometimes used. Sometimes we call it an ancillary qubit, sometimes a check, sometimes a stabilizer, sometimes a syndrome. They all mean the same thing. Okay. So in this graphical representation, we have the qubits, and then this check, the stabilizer is essentially another qubit that's going to help us measure where errors may happen. So let's assume that a single error happened. So this 0 got flipped. So it's the third bit. And so what that means is that after we do that, we will have the following split. So we flipped the third bit, and notice how it flips both parts of the superposition. And so now when we measure the syndromes, we'll see that, so we're basically comparing the neighbors, right? So the syndrome values that we'll see will be +1, -1, -1. Right? So if they're the same, then when we measure the product of ZZ, right? So for this branch of the wave function, we'll see that it's 0, 0, so ZZ is measured to be +1. For this branch, they differ, and actually it also happens over here. So we'll measure the stabilizer being -1. That makes sense. So stabilizer value. And this would be more concrete. And then V1, V2, V2, V3, V4.
Is that XO?
Yeah, it's exactly an XO. And just want to make sure that people, yeah, I think some people look a little confused, so please ask questions. Yeah,
How do you physically move? So
yes, I'll get to that in a little. Yeah, so let's for now just assume that we're able to measure it. Okay. And so then, yeah, so yeah, and yeah, as mentioned, we define some way to actually measure these stabilizer values. That's how we extract that information. And then after we measure these stabilizer values, then we'll put this information into like a classical computer. Monitor. And this guy actually does something called, I'll refer to it as classical decoding. So it will take this information of what was +1 and what was -1 and try to infer where the error may have happened. More precisely, what we'll have is that there is some vector of errors, some matrix that I'll explain in a moment, and then observed symptoms. So what's happening here? You have some errors that actually happen, and then we want to know how each of those errors get mapped into the actual syndromes that we have done. So here, let's just write it out explicitly in this example. So in this example, the error vector was 0, 0, 1, 0. And if we look at how this error will cause the syndromes to change, so an error on the first bit will So an error on the first, or on the third bit, if we multiply this matrix, then we'll get, yeah, so we'll pick out the third column, and so we'll get this object. Does this make sense? No, yeah. Yeah, so essentially, we multiply some matrix on the actual error vector occurred, and this gives us the same as that gives. And so what the classical decoder is doing is trying to say, given observed S, what is the likely E that occurs? Right. So we're trying to figure out what a likely error would be that explains this. In this particular case, there are two different errors that would actually cause this. So this is the error that we said occurred. Another possible error is so I think it would be
1.0.
So you flip both of these and then you flip that. Yeah. So this error actually, when multiplied, would also give you the same observation. And so then, in addition to this, we also want some notion. In order to characterize what's likely, we also need to have some notion of the weights W of the likely error, right? So we're going to say, for example, that each error location has a probability P of occurring, and so therefore it's more likely that this error occurred instead of this error. Everything makes sense so far? Any questions? Yeah.
You started with the smart qubit system of limits. The first step is to make a understanding.
Yeah, so the first step is saying that we encode that 1 qubit into 4 qubits. So everything that is actually happening is always happening on 4 qubits.
But,
And I haven't specified how we achieve this encoding, so that will come later.
after the bit flip, how do I map this again back to the 1 qubit step?
Right, yeah. So that's a great question. So after we do this, and I'm just going to erase this for now. So the classical decoding says, okay, I've decided that the error that probably happened was this. So I'm going to actually do a correction and flip that bit back. So now my resulting state is again a bunch of zeros and ones. So it's exactly the same state as before. And so in this way, I've been able to correct the errors. And if we look at some of our previous criteria, so continuous errors, if this was instead of a bit flip, a small angle rotation, then when I measure these, it will actually collapse it into this type of bit flip error or no bit flip error. The measurement, even though we did some intermediate measurements here to try to catch the error, notice how at the end we still have a superposition. So we did not collapse the logical information, we only collapsed out the errors. And then finally, we never used any cloning, right? Like there was only one A and B. Whereas cloning would be you have like a bunch of A/B coefficients. And so when we actually want to extract the information, for example, if we want to do a logical measurement, then we could say measure in the Z basis and see if we see zeros or one. So I'm going to repeat this this particular sentence here because that's very important. So given observed S, and we have some priors on this matrix H and weight W. The H is also called the parity check matrix. Then the question is infer likely error bars. Okay,
What do you mean by the parallel parity check H?
so we know what we measured.
Oh, so
Yeah.
this is not a prior distribution on H.
Yeah, so the weight is prior.
Oh.
Yeah, so yeah, I guess these are yeah, maybe I'll add that a little bit. Okay, so that's a basic code. This is the repetition code. So now let's try to correct both types of error. And so this is the second one. So this one. Okay, so what's happening here? So we have continuous errors, and we want to correct all kinds of continuous errors. After we do the projection, these continuous errors get discretized. So it turns out, if one goes through the calculation, that we only need to correct X bit flip errors and Z phase flip errors. So a phase flip error takes a 0 plus 1 superposition into a 0 minus 1 superposition. Here we've been able to correct bit flips, but we can't correct phase flips. And so the very basic idea is to use two codes, one correcting each direction. And this particular construction that I'm using to illustrate the surface code is actually a more general construction. Yeah, I guess are people done writing these down?
There's also another one.
Oh.
Okay.
Yeah, we can move this one. I'll move this one a little.
Yeah. A bit of when you want to look at our. So this construction is actually a special case of the more general hypergraph product. So what's in here? We already labeled qubit and stabilizer. So in this graph, in this 2D graph, the circles are data qubits. The blue diamonds are, let's say, Z stabilizers. And the red ones, the red squares, are X stabilizers. So we've constructed some type of code using two repetition codes here as an input. So here, it's a 4-bit repetition code. You have 3 checks checking the neighbors, and then you have like the data qubits, the data bits. And then this somehow, and I'll explain in a moment, gets promoted into a 2-dimension code. And somehow there's some sense in which one of the directions is dealing with your X errors, the other direction is dealing with your Z errors. And although I won't be talking about this much today, this construction actually forms the basis of a lot of more recent quantum LDPC code. So I'll just maybe define that just for people's knowledge, since this is a pretty hot topic in the field. The quantum low density RT check code. What does this mean? This means LDPC. This means that each data qubit has a constant, bounded. Yeah, or let's just say O1. So it's like a bounded by a constant. So as O1 stabilizes, and then each stabilizer has 1 data qubits. And another way to see this, another way to say this is that H is sparse. H is a sparse matrix such that the row and column make up. And so actually this hypergraph product, usually known as HGP. HGP is an important way to construct these LDPC codes. And so you can also see that the surface code that is shown there is actually a special case of this. So let's look at what exactly the surface code is doing. So the surface code, you have a bunch of data qubits, these green circles, and then you have X stabilizers which check the joint X product of the qubits that they touch. So for example, this guy here is checking the product of X's here. And then you have Z stabilizers which check the other direction. So what's the number of neighbors that a data qubit has at most in this example? 3, 4. Yeah, so it's 4 because some of the ones in the middle see 4 neighbors. And the same for the stabilizers, so they only touch at most 4 neighbors. So in this case, this one is LDPC with bounded by this number 4. And I'll mention in a moment why LDPC is important. But for now, this is just introducing some terminology. So we have this surface code here. Let's try to understand a little bit better what's going on with the details. So the first thing we want to make sure is that when we use these stabilizers, we project into some known like subspace, right? So essentially, the way error correction will work is that we try to project it into some subspace of the entire Hilbert space, and then if there are errors that come out of that space, then we'll be able to figure out the errors. So this subspace, so the subspace that we'll work with is the simultaneous eigenspace where all stabilizers
graph, is that like an encoding of the qubit logical?
This is representing the data qubits, the stabilizers, and how the connectivity between the state, like which stabilizers check which qubit.
How many?
So here, for example, there will be 25 data qubits, so 4 by 4 times 3 by 3. And then 12 X stabilizers and 12 Z stabilizers.
So how can I connect it to the repetition code?
Yeah, so in the repetition code, you had 4 bits. Right, and so effectively, if you were to write down a wave function of the quantum code itself, it would be like 25 qubits. Yeah, and I haven't specified how we're encoding yet. Yeah, so this is just like trying to describe what the space is. Okay, and I'll also use use the letter S to denote like the stabilizers. So SC, I guess. Okay. So yeah, so we want this to be so this is how we're going to define our like kind of error correcting subspace. So let's try to figure out what this subspace looks like. And even I actually say simultaneous eigenspace, whereas I have some X operators that I'm measuring some Z operators, these might not commute, right? So let's actually first confirm that this is indeed a valid like set, because we want so let's check if that's the which then will allow us to actually have a simultaneous eigenspace. So, for example, if we have, let's say this check, right? So this is an X stabilizer, this is a Z stabilizer. Okay, so they do have some overlap, but notice how they overlap on 2 sides. So each site gives you an anti-commutation, but because they overlap twice, the 2 minus signs cancel, and so these 2 operators actually commute. Does that make sense, or should I write it down a bit more explicitly?
Please write it down.
Yeah. Okay, so let's maybe just look at this corner here. So I'm going to label the qubits. Okay, I think that should be enough. So I have Z1. So the first stabilizer is Z1, Z5. It was the Z or so Z1, Z5, Z8. And then commutator with X1, X2, X5. So how does this expand? So the Z8 is like just like commuting through everyone. Same with the X2. So it's just like Z8, X2, then commutator between Z1, Z5, and X1, X2. Okay, and then this one, again, we can just separate it because other things commute. So it's the product of so if we explicitly write it out, this is what it looks like. Yeah. So when we pass this X1 through, this x1, when it passes through here, it will generate 1 minus sign. And then when we also pass the x5 through, it will so each of these generates a minus 1. So these two cancel. So therefore, this term is actually equal to that term. And so therefore, this is equal to 0. Yeah. Okay. So basically, when two stabilizers have an equal number of overlap, like two different basis stabilizers have an even number of overlap, they will commute. So we've checked off this box. Now let's try to look at what the logicals look like. So for the repetition code, essentially, we have like this all 0 and all 1. So this logical information, as I mentioned earlier, it should be something that does not get disturbed by these local stabilizer measurements. So we're somehow trying to find something that characterizes the remaining degree of freedom. Initially, we had 25 data qubits. We'll have 12 X stabilizers and 12 Z stabilizers, so we should have one logical qubit. So does anyone have a guess for what the operator for this logical qubit might look like? Let's say the logical Z operator. This should be something that commutes with the stabilizers, right? Because otherwise measuring the stabilizer would collapse it. So what it actually looks like is a product of operators in this direction. So does anyone have a guess as to whether this is the Z logical or the X logical? It needs to commute with all of our stabilizers. And also the Z logical will be like a product of Z operators. So there will be some product on these 4 data qubits. Should it be a Z product or should it be an 50-50? Yeah,
Should be a Z.
yeah, so it should be a Z. And the reason is that, so the Z logical will be equal to Z1, Z2, Z3, Z4. And the way to see this is that there's an X stabilizer here. And we know based on the same calculation that things commute when they touch on an even number. So therefore, in order to essentially this, if we choose this operator, then it will commute with the Z stabilizers because they're both Z. And then it will also commute the X stabilizers because it touches each of them. And this actually one can also show is the minimal number of the minimal weight of any logical operator. So you can multiply a logical operator by a stabilizer, and it will still be a valid logical operator. But this one is the minimum weight. So in general, so we've characterized what this. Actually, I guess I still need to tell you what the X logical looks like. So if we label these, so the X logical is going to be the product in the vertical direction. So what properties did we want the logicals to satisfy? First, they should commute with stabilizers. This one we already established. And second, XL and ZL, like this way, we actually have like a valid logical qubit in the same way that physical qubits operators would need to add. So we can check these two. We see that these two, this logical X and this logical Z actually intersect only at a single point. So that means that they end up anti-commutative. So we do indeed confirm that all of these conditions are satisfied. So we have like our logical operator. Does that make sense to everyone? Yeah.
I think green's like the logical qubits.
So these are the physical qubits. These green ones are the physical qubits. So maybe just to write out a little bit more explicitly some notation. So typically we call a code an NKD QEC code, where N is the number of physical data qubits. So in this case, we have 25 of them. Q is the number of logical qubits encoded. So in this case, we just have one. And then D is what's called the code distance. So code distance, basically, this characterizes in some ways like kind of error correcting power. And the more specific definition is that it's the minimum weight logical operator. Which in this example, I told you that this particular choice of logical representative is the minimum weight one. And the way you can think of why this is connected to the error correcting power is that if a mistake were to happen, then I need to like flip all of those, right? So if there was a logical error that I couldn't detect, right, then what must have happened is that the stabilizers all didn't tell me anything, because like otherwise kind of I would have maybe been able to catch it some way. But so basically it needs to apply something like this product of these. Yeah. And of course, in practice, you're also doing this decoding procedure and error correction. So it's like after you do that procedure, whether something this happens. So here this distance is the minimum weight logical. So this is 4. Yeah.
Okay, so it's like the repetition code also.
Yeah, so in the repetition code, the distance against bit flip errors is also 4. This doesn't mean that you can correct for errors. This only is still just like a definition. And we'll see how many errors you can correct in a moment.
I think like for the repetition code, why do you like encode it with 4 qubits instead of 3? Is it like
Yeah, so you would have more protection against bit flip errors the larger you make the code. Yeah.
So this is going to get this longitude epsilon and XC, but can you choose other edges?
Yeah, so you can choose like other representatives. So for example, if you multiply these 4 qubits, that's actually also a valid logical operator. And one way you can see it is, so I said that like if you look at those 2 conditions, right? If I multiply the stabilizer onto the logical, it's still a valid logical.
Encoded in split.
Because those will be equivalent. So for example, let's take these 4, the product of these 4. If I multiply these 4 Z stabilizers, then these cancel out in the middle, and these 4 become these 4. And we know that the code space has simultaneous eigenvalue +1 for all of the Z stabilizers. So therefore, we know that these 4 products actually will be the same value as these 4 products. So they're equivalent. Exactly.
Maybe I'm just not envisioning it. How would you have, for example, two logical qubits coded in the same, like 25, usually? I mean, how does it not just like kind of half the instance?
How does,
I just can't envision maybe the middle one, like if it was two.
like how to encode two?
Yeah, exactly.
Yeah. So, so let's say that, what's the easiest way to see this? Okay, here's a very trivial example that already illustrates it. Let's say I have 5 physical qubits and I do nothing. I just trust whatever they were, right? Then I have 5 logical qubits. It's just that the distance is 1. Right? So that's a very trivial example. Of course, in practice, you do a little bit more complicated stuff so that you get some protection. Yeah. So, but that's one simple way in which you would get one. Okay. Great. Let's see what's.
I just have like a possibly unrelated question, but I was thinking, so basically we see a surface code with the physical qubits in a hexagonal lattice pattern. Now, are there ways to like encode them such that they're like in a different lattice pattern and then you have different types of stabilizers to have different logical qubits?
Yeah. So in this case, it's actually a square lattice.
Yeah.
You can, for the surface code, you can also have it on hexagonal lattice or other types of tilings. Yeah, so there's certainly quite a bit of design flexibility. I mentioned this hypergraph product and the quantum LDPC codes. And I guess now that I've told you this notation, I can actually say a little bit more about why people have been interested in it. So for the surface code, if you take a more general construction, then, and by the way, this is called the unrotated surface code. There's also the rotated surface code that uses roughly half as many qubits. So for the surface code, for the unrotated surface code, more generally, you can take the same construction and you'll get the number of qubits scaling like this. So for a distance d surface code, you need roughly d squared qubits, and you only have 1 logical qubit. What you can also do is, instead of putting just a simple repetition code, you can put in a classical code that encodes multiple classical bits, right? So this actually is even used in like 5G. For an HTTP with what's called a good classical code input, the parameters that we can get are something like this. So in this case, you still use order d squared qubits, but now instead of encoding a single logical qubit, now you're actually able to encode many of them. And actually the rate, which is the ratio between n and k, is actually constant. So this is of course quite nice. And there are a lot more complex constructions that essentially build further on top of this idea. Yeah.
So you just do this you don't need to do these weird rotations to get the concentration.
So constant rate does not rely on any of those like weird twisted constructions. Those types of constructions and when you want the distance to also be big.
Okay.
So yeah. So this can in principle also scale as the number of physical qubits that you have. That's what's called good quantum LDPC codes. This was like a major breakthrough a few years ago. And there essentially what you're doing is, instead of just directly taking this product, you take a product and then you do some weird twists and mod out a symmetry.
And just, is there any estimate of like the ratio, like of the encoding rate?
Yeah, so in practice, the surface code is usually you go to distance 30, so it's something like 1,000 to 1. For these codes, you can, depending on your regime, typically people are getting to something like between 1 to 10% encoding. So 1% I think is like people pretty regularly get to, and then 10% is if you're like in a very good. So, so I told you a little bit about some of this basic stuff, and maybe one more thing that I'll add here is how to think about logical error rates just in this basic setting. So one of the really important things in error correction is this idea of a threshold theorem, which says that if your physical error rate was less than some threshold error probability, then the logical error rate is let's say equal, yeah, or like scales as some constant times P over P threshold to the D over 2, I think C then. So what's happening here, essentially you so essentially if your physical error rate was low enough, then as we increase the dimension of the system, so increasing the dimension would correspond to increasing D here, the logical errors are getting exponentially suppressed. And so that's very nice, and that's the whole reason why we can hope to get to something like 10 to the minus 12 logical error rate with a somewhat reasonable, not like 10 to the 12 qubits, but like a relatively small number of qubits. And so actually the actual overhead that you're paying, like the D in some sense will scale as polylog of the volume of your whole computation, or like your like target error rate. And so a lot of modern QEC is really trying to like reduce the log factors here. These are still very important in practice, but it's worth remembering that the threshold theorem and basics of QEC cause you to only have a polylog overhead. That's why the whole thing even works in the first place. And then the more complicated constructions reduce this polylog like to smaller polylog power with this log.
Can I ask a very naive question? This is something I never. So the same analogy goes for like classical codes, right? But I can run my computer for days without worrying about polylog factors, or certainly. So what's the way in the classical computation somehow skirts these effects in a way that's fun? That's not.
Yeah, so for classical computers, it already is at a 10 to the minus 12 or 15 error rate to start with. So oftentimes you don't need to run much error correction on top at all. However, in, for example, modern like DRAMs, there is actually some built-in error correction that does some very simple checks at a pretty like macroscopic scale. And so your memory system in I think even in the computer, in the regular laptops, they actually do have some checks to check for corruption. And there's, it actually became a little bit more active topic in the last 20 years as people started building things large enough that you actually do get cosmic ray errors happening. Yeah. In those cases, however, usually you're only using them for memory. So you're storing these bits, and then the computation part typically is like the CPU is only a very small part of all of the data in your classical computer. So I think if I understand correctly, the CPU actually still doesn't use
Hmm.
any error correction, but the memory does, because it's a lot larger and has more time for like things to hit and mess with it. Whereas in the quantum world, our computation also needs to be error corrected. And so that's also why it's a lot more like integrated and core to the whole construction. Okay. So the next thing I'll talk about, this is kind of thinking about things at the basic code level. The next thing I'll talk about is really to look concretely at how this syndrome extraction actually happens. And what will emerge here is thinking about error correction from a more from like a more space-time view instead of just thinking about a code itself. And this is really a pretty recent way that people have been thinking about it. It's actually really natural once you actually write code or think about a concrete problem. But it was only recently that people started formulating it in this way. Okay, so we said we want to measure the ZZs. So how exactly do we do this? One possible circuit is illustrated here. So you have an ancilla qubit initialized in 0, and then we want to measure the ZZ of these two. So therefore we say, okay, if this was 1, then flip it. If this was 1, then flip it. Therefore, if both of them were 1, then this bit will get flipped. So we'll measure some value m1. Otherwise, we'll measure still 0. Right? So this is a circuit, and you can do this with each of them. And so in an actual error correction setting, you'll do multiple rounds of this, right? And the challenge is that each of these could have been noisy. So for example, let's say that I did this and then my measurement had a mistake. Right? So if the measurement had a mistake, then this M1 would actually be flipped. And maybe also just to mention the outcomes, I'll call them +1 or -1 instead of like state 1 and 0, just because it's a D-basis measurement. So what we actually do in practice is not to do error correction just directly on this single layer in time, but rather instead do error correction across multiple time slices and do things that are called detectors, which essentially compare adjacent errors. So a first detector might be the product of the top two measurements, and then the second detector might be the product of like these two measurements. So then if any of them were wrong, for example, if there was a measurement error here, then this would flip this detector. If there was a measurement error here, this would also flip this detector. Okay. So why do we do this? The motivation is essentially that when you do things this way, there will be some region of errors that will like flip a given detector. So for example, if I had like an X error here, right? Then this would flip this bit from 0 to 1. And so this would flip this measurement, and so this would flip this detector. If I had, so I'll call this just like first location. If I had a bit flip error here, right, then this would propagate and flip this measurement, but it would actually also propagate and flip this measurement. So therefore, an error here is actually not going to affect this detector because it flips both of the measurements. An error, yeah, and actually I'll just remove this X2 label now and put the X2 here. So if there was an error here, then this one doesn't get flipped because it's past the C naught, but it will still flip this one. Right? So you'll see that there's some space-time region in which errors that happen can actually flip.
the measurements. So for example, these can all flip it, this can flip it. And so you kind of get this detecting region in which errors happening within this region are able to flip this detector, whereas things happening outside will not. Okay. And it's a local region, so there will be some local things that are able to flip. So given this information, we again want to do this, answer this question, because this will tell us where the errors happened and how to correct them. And this is basically how it will go. So we now will have some knowledge. So we know how errors in space-time. So when I say space-time, I just mean like this is time and then different physical qubits within each logical qubit. So we know how a given error will trigger detectors. And given this information, and we also know and how likely each error is. And so we want to, and then given observed detectors, figure out most likely error. Or figure out likely error. I guess it's oftentimes decoders don't necessarily figure out the most likely one. But figure out likely error. In space-time. So now E, instead of being just like an error on each physical qubit, it will be an error on given physical qubit at a given time location. And so actually then you'll see that this formulation actually is almost the same as our usual code formulation, but now we're directly doing it for like the actual circuit that we're doing syndrome extraction on. Yeah.
It seems like you lose one bit of information because or am I missing something? Because you went from like, if you have T time steps, now you went from T to T-1 detectors. Is there a reason to discard that bit of it?
Yeah, so actually you're always comparing neighboring things and then you initialize them in like say or 0. So there's actually one more detector at the front. So you basically still have as much information as you would need in order to interpret things. There's no loss of information.
Okay, so this is actually in some sense just a convenience to make the decoding entirely local in space-time, and that should make this error, like this likelihood problem, easier to solve. Is that the way?
Yeah. So I think there's in general no known systematic way of constructing detectors for like completely generic problem to make it local, but oftentimes you can do it pretty just comparing neighboring measurements. Okay. So in this circuit, we've been looking at X errors so far because this is the basis that will trigger the measurement results. And actually, I guess I wasn't using consistent colors because Z stabilizers are the ones that actually will get flipped by an X error. So yeah, but let's say there was a Z error, and let's take a look at what will happen. So if there was a Z error here, then this Z error will actually so the Z error will actually spread through the C0. So yeah, I guess actually maybe let me just write down the C0 propagation rule that if you memorize one thing, you should memorize this. in QEC. So if you have a C naught, then X propagates into XI propagates into XX. X on the bottom is still X on the bottom. And then it's opposite for the Z. This is like basically every day you're reasoning about this. So it's really important to remember this. Yeah. And you can verify yourself later on that this is what happens. Also, actually, maybe to mention a really useful tool. There's a tool called Quark, developed by Craig Gidney at Google. It's a drag and drop circuit simulator, which is super useful when you're doing like small circuit optimization or like just trying to understand a gadget. Yeah, so we actually use this super regularly. And then there are also a bunch of other tools. Maybe since we're on that topic, I'll also just mention this is basically implemented in STIM, which is like another package that Craig Gidney developed for QEC simulation. Super useful, like pretty much everyone in the community uses this now. And then there's also a visualization tool called Crumble that they developed, which is also super useful in visualizing circuits. Usually when we do quantum error correction circuits, we usually go and like just look at, yeah, I can actually maybe tomorrow just show what these tools look like. I realized I forgot to prepare an example of that, but I'll do it in the next lecture. It's kind of fun, yeah. Great. So, okay, so here, sort of coming back to this. So this Z1 will actually, through the C naught, actually propagate into a Z on multiple qubits. So through a circuit, you can actually propagate a single error into multiple errors. And in particular, in this case, we propagated a single error on the ancilla qubit into multiple Z errors on the data qubit. And you might imagine that this can be bad. And this is actually one of the main reasons why we consider quantum low density parity check codes. Really, the main motivation is to limit error spread in syndrome extraction circuit. Yeah. So essentially, if you had a bounded weight, then the amount of spread is basically limited by how many data qubits you're touching. And so things won't spread too bad. And so that's how you have some guarantee that you'll still get good performance when you go to the actual circuit level implementation. Any questions so far?
Sorry, but then it also depends on the dimensionality, because if I touch 3, but each of those 3 touches 3, won't I have like still a big?
Yeah, but during this time, you'll start getting error correction with information, and so like basically, you want there to be limited spread between each time you get to learn where the error. Okay. Yeah. So I guess maybe this was 2. This, I guess this kind of space-time view is kind of 3. And so now let's just concretely look at like what an error correction actual experiment might look like. Like probably everyone heard about this Google surface code experiment. What exactly are they doing? So what they're doing is what's called a quantum memory experiment. So what you do is you initialize data qubits. These are physical qubits into 0 physical. And then you measure stabilizers for many rounds. And then you measure data qubits in the Z basis. Okay. So this is the memory experiment. Maybe a few comments to make. One, it's this particular experiment is only one basis. So oftentimes you also do it in the other basis. And it's also only looking at a Pauli logical state. So we prepared like a Z eigenstate and then trying to preserve that. Second, and this is like a common misconception for when one is just starting. So often you might hear that you need feed forward. There's actually no feed forward in this experiment. Earlier on, I drew it as like, oh, we do this decoding and then we like do some kind of classical feed forward correction. In practice, you actually don't need to do the physical correction. What you can do is track the errors in software. So for example, if you determine that, oh, I made a mistake here and I should flip the qubit and apply like an X operator, you just keep track of that till the end. And then when you interpret your final measurement result, you say, okay, like this should really have been interpreted the other way. So this experiment actually has no feed forward. And I'll mention later on where the feed forward actually comes in. Yeah. Oh, yes. Feed forward means conditional on some measurement results that you did before. You do a conditional gate on the other qubit.
Correct, yeah.
To either correct the error or to do some other operation. Yeah.
That happens like mid-circuit.
Yeah. Okay. And so yeah, so this really is a basic characterization of your system. But the reason that this is a good benchmark is because it in some sense characterizes the basic, like being able to keep the information alive, characterizes the basic QEC capabilities of the system. Like you're just trying to correct the errors. And then also many gates can be built out of this. So just by being able to do like this basic capability of doing repeated rounds of error correction, you can actually start building some gate operations. And that's the main thing that I'll do. Any more questions so far? Yeah.
What are the advantages of low density parity check versus like cyclic parity check?
So these bivariate bicycle codes, they're also low density parity check. The bound is 6. So most of the QEC codes that you'll see people using like at the base level, those usually are frequency codes. The only exception is concatenated codes, which effectively have higher weight. But that higher weight is through the concatenation levels.
Well, I have the tracking this errors in software until the end. This is for ITAMP root shot, right?
What do you mean by ITAMP?
So like if you run the circuit once and you get it out, but say like if you didn't write it to like a single measurement,
or some true value about whether or not it worked. And you want to measure your entire register. Do you perform with one error correction on each run or the collective?
By each run, do you mean like this counts as one run?
Like
Or
the
like the whole circuit?
whole circuit.
Yeah, so it's per run, yeah. So in this given run, you want to know where the errors occurred in this given run. And so you do decoding and everything. So does that?
Yes.
Yeah. Any more questions? So now let's do gates. Okay, so I'm going to draw, so I'm going to draw now, again, the surface code. I'm going to draw a slightly larger one. And we'll see how this allows us to do gates. So this is now a long surface. It's 6 by 3. And so let's actually imagine that at first it was 2 surface codes. So at first you only had this half of the system or this half of the system, like just separately. So there were no qubits here. The checks are just the individual patches. And now let's add in qubits in the middle, in which these were initialized in plus. Actually, these are initialized in 0. So these new qubits along the middle were initialized in 0. And you also start measuring all of these new checks. Okay, so just to write that out. 2 logical qubits initially in surface code, and then this is like distance-free surface code initially. Then we start measuring joint checks. And then we measure this for, and we start measuring it. So let's see what happens. Okay. And by the way, what I'm explaining now is, I guess, doing gates. And this particular one here is actually what people call lattice surgery. So start measuring joint stabilizers. So now there's like effectively, there's only 1 logical qubit, right? So we used to have 2 logical qubits, but now it's just, you can just think of it as a big patch, right? So there's only 1 logical qubit. So how did 2 become 1? Well, it means that essentially there's some information that now got projected out as well. And in particular, if we look at the values of some of these stabilizers, so previously, all of the stabilizers within each half of the system were known. We initialized this one in 0, so therefore the product of these 4 we also know, right, because it was initialized in 0. So these blue checks are also still valid. The checks that we added are these red checks on the scheme. So the red checks here initially, they were just some completely random value, and we don't know what they are. But the product of red checks is actually equal to the X logical operator of the two logical qubits. Right? We saw that the X logical stands vertically. And so if we multiply these three checks, right? So this one will touch these three, this one will touch these four. So this one cancels out in the middle. And so you can easily convince yourself that the product of red checks in the middle is actually equal to the product of the two logicals. So in other words, the reason that we've lost 1 degree of freedom is that we've actually effectively done a joint logical measurement of x1, x2. That's how we start from 2, ended up with 1, because we essentially measured out 1 degree of freedom. So what does this achieve? This actually, when you measure a joint logical, this projects you into an entangled state. So for example, initially, if I had a logical qubit that was 0, 2 logical qubits, both of which were 0, and then I do this joint XX measurement, then the output state is actually going to be a bell pair, where which bell pair it is determined by like essentially whether the XX measurement came out +1 or -1. Does this make sense? Because essentially previously ZZ was an operator that stabilizes the state. ZZ commutes with XX, so it's still in that eigenspace, but now it's also like an eigenstate of XX. So therefore it's one of the bell pairs.
What a bell product state of plus.
Yeah, so a bell pair is like 0, 0, +1, 1, or like 0, 0, -1, 1.
Why is this not like 0, 0 + 1 times 0 + 1? Because you're applying 2x operators.
So you're measuring the product.
Oh,
Yeah, so you're never measuring them individually, so you actually still don't know individually what they are. And that's why they get it. Does that make sense? So through this, we've been able to do an entangling operation. And what state you project in, or the logical measurement result, is the product of these checks. But each of the individual checks can be noisy, right? And so therefore, so essentially, logical measurement result is in the noisy checks, right? It's just a product of some of them. So therefore, we typically want to repeat this measurement d times so that we have enough protection against the errors that.
And the intuition for that D is that you get the same protection as the distance of the original.
So it's a measurement, how is it a unitary, how do you get a unitary gate from?
Yeah, so you can construct a C0 gate between 2 qubits by so you have like qubit A, qubit, let's call it 1. So you have qubit 1, qubit 2, and then if you use an ancilla, then by doing some joint measurements and some feed forward, you can actually do like a C0 gate between these two. Yeah. So within those qubits, because you never measured out their information, right? So you can actually do a unitary gate.
is it like in the physical qubits, I'm having a measurement, but logical it's actually in the unitary. So I mean.
And the logical, so this joint XX is a logical measurement. So it's more like you first entangle these two, and then you entangle these two. But like the actual information never got that. So you fed and recognize it. And I guess homework will be use quirk to figure out what exact measurement, because I don't remember. Actually, like simple heuristic to try to figure it out. Okay, let's try to guess what the circuit will be, and then the thing that we need to use quirk to figure out is what the correct feed forwards are. So for genericness, let's just put in a 0 here. It probably doesn't matter. If this was a joint ZZ measurement, then we would have figured out what the top one is, because we already know the bottom one is 0. Therefore, this should be like an XX joint measurement. And then if this was a joint XX measurement, this one probably shouldn't be a joint XX, because then you figured out the parity between Q1, Q2, which is not what you wanted to do. So therefore, this is probably a joint ZZ measurement. And then you want to measure this in the X basis, because otherwise, again, you figured out that what the bottom one state is. And then you need to do some feed forward such that it actually doesn't see it. Okay, so this is one type of gate. It's somewhat complicated, requires D rounds. So the other type of thing that you can do is what's called a transversal gate. And I'll just only show the C0 gate. So in order to do a transversal C0 gate, we'll do transversal C0 is just physical C0 between each pair of corresponding qubits in 2 code blocks. You have a surface code, you take 2 surface code, you just like literally do the physical C0 on each corresponding pair of qubits. And this turns out that it will do a logical C. How do we see this? So we already memorized how things propagate at the physical qubit level, right? So a single X propagates into XX. If you had 2 code patches, both of them surface code qubits, the X logical on the first one, if you just did the same thing everywhere, that will just get copied over to the X logical on the second one. And so therefore, you've copied the logical information just literally directly. That would do a C0 gate. And you can easily convince yourself that it still commutes with all of the stabilizers are still valid. And so you indeed still have a valid code. So this gate was actually the first gate that people proposed. But it kind of got a little bit lost over the years compared to lattice surgery, because this one, as you might imagine, if you want to do something like this, then you can't do it in 2D. But now we can with like neutral atom hardware improvements, with trivions also, you can really start to do these types of gates. And so in many ways, it's actually like a much simpler way of doing gate operation. And in particular, one of the main things is that you actually only need O1 stabilizer rounds. So basically, because you directly copied that information, right? So really your error correction, your stabilizer measurements are no longer carrying logical information. They're truly just being used to like catch errors. So in other words, this is because stabilizer measurements are only used to catch errors.
And not for logical operation. This fact that you only have, you only need to have one order one stabilizer around, actually was like, it was only basically last year that we proved this, and that it works actually pretty generically, even with universal computation, when you also have like forward operations and whatnot. So even though this construction is very basic, because people had kind of forgotten about it for a while, a lot of the key understandings actually were only developed basically within the last year. But I think it's a very powerful method, because if you compare this, you need to repeat D times here. And in general, for large scale problems, people are typically quoting D of around 30. So you really have a significant improvement in your time, your time cost of error correction by doing something like this. And so the effective logical clock speed that you get can actually be a factor of 30 or so faster if you're able to use transversal gates. So this actually allows you to do what's called Clifford operations. So maybe for the last part, I'll just define what Clifford and non-Clifford are, and show some very basic stuff about that, and then I'll leave the rest to the last lecture, in which I'll also be showing some of the recent magic state distillation results from Clara, which exemplify and tie into some of these Clifford and non-Clifford operations. So, okay, so the last thing that I'll talk about is what Clifford and non-Clifford mean.
I need more space, maybe turn over here.
Yeah, I think I'll actually be able to just fit it in here. So we know what Pauli's are. Pauli's are X, Y, Z. So Cliffords are unitaries such that U dagger Pauli U is equal to some other Pauli. So it maps Paulis to Paulis. So this is also known as like an operator in the second level of the Clifford hierarchy. So what's an example of this? If you have the block sphere, and then you like rotate around the z-axis by 90 degrees, right? So then x gets mapped into y, so that's a Clifford operation. And it turns out that C0 is also, so like in terms of gates, C0 had a mod S gate. So S gate is 90-degree rotation around Z. H maps, so H maps X to Z. And then this is like a 90-degree. And I guess I didn't actually define the C0 gate. The C0 gate is like, if the control was 1, then you flip the other bit. If it was 0, then nothing. Okay. And you do it in superposition. Okay. So this is the Clifford gate. It turns out that these Clifford gates actually form a closed group. And the way you can see that is, for example, if you just look at a single qubit, rotations with 90 degrees, they only rotate you between these discrete directions. So it's pretty clear that it's closed. And so then you can actually go up in this hierarchy. So this is like level 1, this is level 2. So the third level will be something that maps Cliffords to Clifford. So I'll actually change my letter here from U to C for Clifford. So the third level is a unitary that maps Paulis into Cliffords. So you essentially go one level up. And an example of this is a T gate, which is like a 45-degree rotation
around Z. So there's this very clear hierarchy of structures. And it turns out that Pauli gates you can do in software. Clifford gates you can typically do with transversal gates pretty reasonably in like a lot of the codes. And then these T gates are harder to do. And that will be the topic of the last lecture. Yeah, and actually this structure, maybe one thought, this structure here will actually also turn out to be important in order to be able to teleport the gates in. So, and I'll talk more about that.
And so it's easy to come back.
They're pretty similar to like, I know, to parent data qubits. Right now for neutral atoms, we do not reuse the qubits. So for example, if you measure one, then right now you would just have one less qubits to use. But that's actively being addressed.
The second question is a lot of codes that I'm seeing now, where's the full circuits that I'm thinking, really like to use arbitrary phasor where like for each degree of like each additional degree of binary precision on those phases, it requires more than T gates.
Yeah.
Is that something that we covered?
I wasn't planning to cover that. That's kind of a whole separate area of like synthesis of rotations. Typically the methods have log1 over epsilon scaling in terms of the amount of resources used, the number of T gates. But that is like a very important separate area. It's more connected to algorithms in some way, which is why, yeah, but I'm happy to like discuss the topic. Yeah.
Gate operation over here, are you using stabilizers to perform gate operation?
Here or here? Here. Yeah, so here you're measuring stabilizers, and with that information, you end up like getting logical information out of it. Yeah.
So then stabilizers are now like a logical gate.
Yeah, the stabilizers help you implement a logical game.
Yep.
This one. This one. No.
Still depend on physical
Yeah, so if you repeat D times, then essentially the way you can think of it as here, if we just look at a single slice and assume just data qubit errors, then it's only when after you do your correction, the chain of errors spans across that a logical error happens. Here, if you just like look at like the space time of this, then it will be either an error that spans across time or across space. So if you repeat it D times, then you still need D errors in order to get a logical error, which means that you get this D to the D over 2 type expression. You measure all of them. So you measure all of the stabilizers, not just at the boundary.
But actually you're measuring like all of these.
No, you're not measuring all pairs. So these are the original stabilizers, right? And then you add 3 stabilizers in there. So those are all of the stabilizers that you have in the system, and you repeatedly measure all of them. Yeah. And so, for example, if there were to be like an error in the space direction that happens, in order for it to not be detected by these stabilizers, then it would actually still need to span across the whole system. And that's how you get like the scaling with the error suppression. Yeah.
Keep actually without with the parent state, the same state. But
Yes.
Okay.
Correct.
Okay.
The two pupils here are those two 3x3 surface code.
Yes.
But then what's like the central that is,
So these are some ancillary physical qubits that you added.
that the central zero state that you.
This is when you put it in, when you initialize these two new ancillary qubits. I guess they are actually data qubits, but when you initialize these two new data qubits, what state you should initialize them?
But aren't you essentially entangling those two new data qubits, like how are those two surface cables?
Yeah, so essentially, these two surface codes get entangled by like getting merged into one. So you have these, right? So this stabilizer like is measuring all three qubits, so it's kind of entangling them together. And then same here. And the entanglement kind of goes through these qubits to like, so the whole thing gets entangled. Yeah. But yeah, like as I was mentioning, essentially here what you have, right, is just like a big surface code. And the big surface code is long range entanglement if you measure it d times. So you know that there's long range entanglement getting established through the measurements. Yeah, but here's another intuition that might help. If I do these measurements and then feed forward, then essentially the measurement plus feed forward is like almost like teleporting information. So that's how the information, even though the measurements are happening locally, is able to like produce long range entanglement.
It's the same measurement, the time,
Same measurement.
it's not projected measurement, you don't get the same state.
So it is a projected measurement, but there's errors happening still during these measurements. Yeah. That's why you need to, yeah. If all of your measurements were perfect, then you would not really need to
Get the same result.
if you had no errors. Yeah. So if you had errors, then you'll get different results.
Good. I think it was a really fantastic lecture. So will be more questions, I am sure, and there's also the opportunities during dinner, which is in half an hour. Yep. So join me in thanking Harry and Francisco. We will I think the lecture room will stay open overnight if you want to, work, whatever, here. And we will reconvene here tomorrow at 9 o'clock. And breakfast will be again at 7:30. So in half an hour, we'll see each other for dinner. Good.
So just let me quick, do people prefer the whiteboard or writing on the iPad? So that what?
So either way.
You choose. You choose. We don't ask the students how.
I'm a magnanimous dictator.